This is a question on exponents, which I saw in a GRE practice test. And this asks for the least integer value of n for which 5 to the power n is greater than, this is a pretty big number, it's 105 followed by 5 zeros. And it's a multiple choice question, so we have to select the correct answer. Now, a solution of a similar kind of problem that I saw on the internet actually asked for finding the square root of that big number that's given, to reduce it, and so on. And that seemed like a little bit longer way to me to do this, because it involves finding the square root, which takes some time, and it didn't seem a very direct method. So the solution that I'll describe here may be a little bit more time efficient, because if this question is on GRE, which is a timed test, you want an approach that will help you solve this quicker. So let's first consider the number that we're given, and it's a big number, but it has got a lot of zeros. And whenever that's the case, you basically count the number of zeros that are there in the end, and that is basically, in this case, 5 zeros. So you have 10 raised to the power 5 multiplied by, whatever number is before the zero. So here before the zeros we have 105. So we can express this big number as 105 multiplied by 10 to the power 5. And then we basically break up 105 and 10 into 5 multiples of 5. So what's 105? 105 is 21 multiplied by 5, and then 10 is basically 2 multiplied by 5. So this is what we have here. So 21 multiplied by 5 multiplied by, within parentheses, 2 multiplied by 5 whole to the power 5. Now if we remove the parentheses, we basically have 21 multiplied by 2 to the power 5, and then the exponents on 5 get added, so we have 5 to the power 6. Now 21 multiplied by 2 to the power 5, that is 21 multiplied by 32, and that comes to 672. So essentially we reduce this big number to 672 into 5 to the power 6. And this is not really much of a reduction, but it's basically expressing the big number in a different way, in a way that's convenient for us. And here we are mainly focusing on expressing it in terms of higher powers of 5. But we still have 672, and we need to see how to deal with that. So we know that 5 cubed is 125. That's pretty straightforward, right? So 5 to the power 4 will be 625. Now, what about 5 to the power 5? Well, we really don't need to know what it is, but we can easily tell that 5 to the power 5 will be greater than 672, right? Because if 5 to the power 4 is 625, which is just short of 672, then 625 multiplied by 5 is surely going to be greater than 672. So we can write 5 to the power 4 less than 672, and 672 is less than 5 to the power 5. Now if we multiply all sides of this inequality by 5 to the power 6, and since 5 to the power 6 is a positive number, our inequality is still preserved, right? So on one hand we have 5 to the power 4 multiplied by 5 to the power 6, so that's 5 to the power 10. And then in the middle we have 672 multiplied by 5 to the power 6, so that's kind of my big number here, right? The number that we have been asked to compare in the question. And then on the extreme right side I have 5 to the power 5 multiplied by 5 to the power 6, which makes it 5 to the power 11. So we find that this big number that we're given lies between 5 to the power 10 and 5 to the power 11. So the value of n for which 5 to the power n will be greater than this big number will be 11. So moving on to the next question, and this is an interesting question that has been again asked in various standardized tests, different variations of these may exist, but the method essentially will be the same, or the approach will essentially be the same. So how many positive integer factors does factorial 10 have, excluding 1 and factorial 10 itself? So factorial by definition is the product of all the numbers, all the integers, consecutive integers starting from 1 and going up to right up to that integer. In this case, factorial 10 will be the product of 1 multiplied by 2 multiplied 3 all the way till 10. And I've excluded 1 here because 1 multiplied by any quantity doesn't really change the quantity. So I started from 2. And one of the things that we need to do whenever we are asked to find factors of a number is to really break down the number into its prime factors. And here, in this particular case, we have a number of prime factors already. So 2, 3, these are prime. But then the non-prime factors, those are the ones which I have, indicated in colors. So in those cases, in this particular case, those non-prime factors are 4, 6, 8, 9, and 10. And our next step is to convert these non-prime factors into its constituent prime factors. So 4 becomes 2 square, 6 is 2 multiplied by 3, 8 becomes 2 to the power 3, 9 becomes 3 square, and 10 becomes 2 multiplied by 5. And now we just have a combination of the prime factors 2, 3, 5, and 7, and we can find how many of each prime factors are there by simply adding the exponents up. So when we do that, it becomes 2 to the power 8 multiplied by 3 to the power 4 multiplied by 5 square multiplied by 7. So once we have reduced the number to basically its prime factors, we are in a position now to find how many different factors does this number have by considering how many selections can we make from these constituent prime factors. And I just break down the problem in a different way here. What we consider is, if we are given 4 categories of numbers, so 2, 3, 5, and 7. In the first category, that's the category 2, we have 8 2s to choose from. In the second category, we have 4 3s to choose from. In the third category, we have 2 5s to choose from. And then in the fourth category, we have just 1 7 to choose from. So the question is, in how many ways can we potentially select different combinations of numbers from this set. So let's start with the first category. So that's the category of 2. We have 8 2s. Now we can potentially select only 1 2. We can select 2 2s. We can select 3 2s. And we can go all the way up to 8 2s. So that's 8 different ways. But we can also choose not to select any of those 2s. So a total of 8 plus 1, 9 ways for this category. And the same logic basically applies to each of the other categories as well. So for 3s, there are 4 3s, so that's 4 ways. Plus, we can always choose not to select any 3, so that's why you have the plus 1 there. 4 plus 1, 5. And similarly for the other 2 categories. Now, if you multiply these, we basically get the number of ways in we can choose different combinations from these 4 different categories, and that's going to be 270. So that gives us, the number of potential factors we can generate by different combinations of the primes that are present in factorial 10. Now, one thing to note will be that this 270 does include the option where none of 2, 3, 5, and 7 are selected. And that basically accounts for the universal factor 1, because we haven't chosen any of those primes 2, 3, 5, or 7. So that particular option may account for the universal factor 1. And then there's the other extreme also included in this 270 number, which is basically the option where we have selected all the 2s, all the 3s, all the 5s, and all the 7s. So basically we have selected, this option, we just includes the number itself, right? And going by the question, it asks to exclude 1 and the number itself. So if we just subtract 2 from 270, we'll get 268, which in this case is the number of integer factors of factorial 10, excluding 1 and factorial 10 itself.